thanks Professor Renzo for the introduction. Also, thanks Professor Zhou for the invitation. So I would like to use this chance to introduce our recent progress on these simulations of Janus droplets in shear. So the outline of my talk is like this. I will give some background introduction, then I will show you some numeric methods we recently developed. Then we'll give some discussions on two kinds of problems. One is deformation and rotation of 2D Janus droplet. Then we have the three-dimensional simulations. Finally, we'll come to the conclusion and perspectives. Okay. Just now, Professor Montati have given a brilliant introduction about the multiphase flows. Here, I would like to emphasize that for all these multiphase flows, the importance is about the dispersed phase. The dispersed phase could consist of solid particles, bubbles, or droplets. All these kind of brilliant multiphase flows you can find in nature like sandstone or in the wind-snow interaction or in industrial applications. I don't want to talk too much about this. Just now, Professor Montani gave us show that people actually in industrial applications would like to use like a single fluid formulations, like a two fluid model to do the simulations. That consider the dispersed phase flows like one fluid simulations. In these flows, I would emphasize that also Professor Montati have emphasized the closed model for this phase counting is very important here. So for examples, what's the effective viscosity of emotion here? It depends on the size of the particles. It could depends on the volume fraction. For example, here I list a particle in the paper prepared by Professor Gosley and Polik, and they published in JFM in 2018. So that shows the previous study regarding this theoretical analysis, what the model can be used to approximate the effective viscosity with particular flows. But for the droplet, recent research also showed that it's not only depends on the volume fraction of these droplets, also the viscosity of the droplet is equally important. So for us, we think how to understanding these macroscopic flows at the particle scales is also very important if you want to have some accurate modeling of this interface interaction model. For example, if you have these informations, it would be very useful to establish this fast coupling or this closure model for the two fluid models. For examples, for the macroscopic flows, actually for the ellipsoidal particles in shears, the studies can be traced back a long time ago, up to like Jeffrey in 1922. It's well known that he has a very famous research that's Jeffrey Orbis. He obtained an analytical expression for this trajectory of particles in shear flow. That means the trajectory can be described by the shear rate gamma, aspect ratio of this particle lambda, or the polar angle, and the azimuthal angle phi can describe the orbits. So the Jeffrey orbits can be described by constant c here. Also, the rotation period of the ellipsoid can be, for example, TP here can be a function of the gamma, also the aspect ratio of these particles. We know that the particle would rotate in the shear flows, but for the pure droplet, they have a very different dynamics. They don't undergo rotation in shear flow. Instead, they have a steady deformation or eventual breakup, as we show here. Okay, so this is quite fascinating results here. Here we consider a different kind of droplet, that's Janus droplet. The Janus droplet means the droplet consists of two immiscible component droplets. These droplets are share an interface, they are in contact, and can have wide applications as I show here. For example, the magnetic ions for the catalysis or biological analysis. Okay, Even for very simple configurations like showing on the right figures here, for the ideal Janus droplet, that means the volume and the shape of the component droplet are symmetric. They can behave like a simple solid particle with broken Fourier and after symmetry here. They have some analytic solutions and show very interesting dynamics there. Sorry, I think my movie is on here. I need to continue. Come back, sorry. So in our simulations, we consider this Janus droplet because you can have many more parameter space, like you have a different volume of the component droplet. You can have different density, viscosity, or subtensions. So the dynamics of Janus droplet in shear could expect very complicated behaviors here. So here we consider this flow mechanism about the rotation Janus droplet in shear flows. In particular, we are focused on the deformation, rotation, and coupling. Also, we want to study the orbit dynamics of Janus droplet in shear. On the other hand, because such a ternary fluid, because such a Janus droplet would involve three different kinds of fluids, also pose challenges to numerical methods. So we are showing some numerical methods here. The method we call it is improved fast field model. I don't know if the audience are familiar with the interfacial capture method. Generally, for this kind of methods, it's very popular in simulating fluid interface. They use scalar functions to track the evolution of the interface here. The popular ones are the volume fluid methods, left-side methods, and the fast field methods. Okay, especially for the left-side method, they use a scalar. We call it sign dysfunction to represent the interface shape and the position. But for the fast field methods, the volume fraction with hyperbolic tangential distribution is used to track the evolution of the interface. But for this interface capture method, one of the challenges is that because of the non-uniform flows, it always makes the interface profile deviated from its equilibrium state. For example, for the left-side methods, the scalar, when it's at equilibrium, it should have the property of sign dysfunctions. But when the ununiform fluid distorted this profile, we have to use some artificial process called reinitialization to restore it to the sign dysfunction. For the fast field method, it's supposed to have the hyperbolic tangential distributions, but also because of the non-uniform flows, it will make it the deviated form. We have also have some functions to restore it to the the equilibrium state. For example, the popular fast field model is the Canadian methods here. In addition to this advection of this material interface, we have the fourth order diffusion term on the right hand side here. Actually, these fourth terms actually from oriented from the gradient theory of interface from the macroscopic state, like also based on the thermodynamic theories here. However, for the macroscopic flow simulation, as we consider here, or the diffuse interface model, actually this term actually ensure the interface go back to the equilibrium state. Here we have the epsilon here. The epsilon denotes a measure of the interface thickness. We have diffuse interface here. That means the interface is replaced by a finite thickness of a mixed layer between two fluids. Also, if the interface is in equilibrium, then the right-hand side should vanish. Then we would have this chemical potential should equal zero. Then we can derive for a flat interface, have this hyperbolic tangent profile here. For diffuse interface model, it's very important to have sharp interface limit. That means when the thickness of the interface approaching zero or the epsilon goes to zero, then the right-hand side of this equation should vanish as well. To ensure these properties for the Canadian model, then we would have the mobility here, the M should have a scaling of epsilon square, this order. The advantage of the Canadian fast model is that it's very simple. It's very friendly for the fresh newcomer. And it also can maintain the volume conservation. When you calculate the subtension, it's all very straightforward and accurate. But it also has some disadvantages, like it's very difficult to keep the interface in equilibrium. Also, it also has some kind of spontaneous shrinkage. That means when the radius of your bubble or droplet have the same scale as the interface thickness, the bubble apparent to disappear in the fluids. We call spontaneous shrinkage. Also, because of the fourth order diffusion term here, if you want to use explicit schemes to discretize the Canadian model, you need very, very small time steps. So in order to avoid it, neurally implicit or semi-implicit scheme is used for the discretization of Canadian model. Regarding these disadvantages, we propose an improved fast field model. Similar to the Canadian model, we also have a right-hand side terms here. Here, this is a second order term. Okay, the importance is we have a nonlinear coefficient Kc here. This Kc actually is provide a measure of the state of the profile. How to say this? For example, if the interface in equilibrium, then we would have zeta equals 0. Then the sign of the zeta is associated with the state of the interface profile. If the interface is thickening or is elongated, we want to goes back narrowed, then we expect that this zeta should be negative. Otherwise, it should be positive. So also the magnitude of zeta reflects the degree to which the interface profile deviated from equilibrium. So that's the three principles this nonlinear zeta should hold. So how to define this zeta? We know that at the equilibrium, the gradient of C should have such a analytic solution for this hyperbolic tangent function. So then we propose the zeta should have such a form like this. So then we can straightforward to get this, the diffusion and coefficient should satisfy, and it's very simple to get that, the three criteria in the previous slides. Then we have where zeta equals 0, then it's naturally to have this hyperbolic tangent profile of the interface. That's the interface at equilibrium. It's quite straightforward here. So actually, this model like this, we has similar models have been proposed previously. I gave a list here. Then go back here. Then we make sure that how to choose zeta to make sure the interface go back to this equilibrium state. But the mobility though is very important because we want to make sure that when the thickness of the interface go to 0, then the right-hand side should vanish. That means it reach the sharp interface limit here. How to make sure that? Then we do some scaling analysis here. For example, on the right-hand side, we have zeta. Zeta in this form is have order 1. But the gradient of C, here we have the order of epsilon minus 1 here. So we have these two combined together. Then we have this epsilon minus 1 plus kappa. Kappa is the local interface coverage. Because in the numeric simulation, that means all the interface should be resolved, no matter how small of the coverage, how the radius of the coverage small at S, it should be resolved. So we think that the kappa here should be the L over 1 over L here should be resolved here. Then, according to this scaling analysis, we can obtain that the mobility should choose like order of epsilon square. So then here, lambda is a constant with the dimension of the inverse of time. Okay. So another issue is the unresolved droplet bubbles. Okay, the initialization process of the interface to the equilibrium state can be viewed, for example, for a small bubble or small droplet. We can see as a solution of a one-dimensional equation as following. So for the Canadian model, we have the 1D equation like this. We can see that when R goes to 0, that means the radius of droplet goes to 0, then this term, R 1 over R, becomes more and more important. So that's the reason why the spontaneous shrinkage occurs, because you cannot get an analytical solution as the interface profile shows here. But for these modified or improved fast field models, we don't have this 1 over R here. So that means even if R goes to 0, doesn't matter. So we still can get the solution of the equilibrium state here. Okay. So in other words, on the result interface, such a very tiny droplets bubbles can exist using this improved fast field model. So now we come to these governing questions. This is a Navier-Stokes question for incompressible fluids. Here we have the Fs. Fs is a subtension. Okay, the G is the gravity here, and then we use the improved fast field model for the interface capturing here. So this consists of the governing question for our numerical measures. Another thing I need to mention is about the subtension calculation. Because we use the continuous subtension force, that means we replace the singular force at the interface by a volumetric force in the governing question. What we do is we use this smooth dirt function here. Because the dirt function should be related to the position of the interface, because the wear subtension play a role. We propose this delta N in this shape. This ensures that no matter what the distribution of the interface profile would be, out of equilibrium or at equilibrium is always ensure that this integration equals 1. This is quite important here, because, for example, for some cases, if you use the delta 1 star here, when the interface is out of equilibrium, then you cannot have this the function property here. That means integration of this function cannot equals to 1. That means your calculation of subtension is not accurate here. So the N depends on the number of N. Actually, the concentration of a subtension varies. The larger the number N, the more concentrated the subtension calculation, as we show here. Okay, here I give you a summary of the numeric scheme. Here we have the Crank-Nixon scheme for the viscous term in the Navier-Stokes question, or the moment question, or the Dam special force for the convective term. And we know scheme also used projection mass for the coupling between pressure, and also the third order Runge-Carter mass for timing integration. So we also use the staggered grid for the discretization to make sure that the divergence-free velocity can be obtained here. Okay, now he shows some validation cases. The first one is radial instability. That means when a heavy fluid is placed on a light fluid, any perturbation in the phase would cause this kind of numeric instabilities. People usually have interest at the front of this spike and also the front of this bubble here. So previously people have done extensively on these issues. So we use our numeric results as these curves, solid curves here. So compare with other people's results, we can have quite a good agreement with them. The second case is a rising bubble in water. So due to the buoyancy force, the bubble is going up. So here we show the results, for example, in the interface profile, as you see here, there's the contours of the volume fraction here. And this at the time of 0.8, on the right-hand side, The curves are our results. These symbols are from the reference. That's the paper published a long time ago. At the t equal 1.6, we can see that actually this bubble would have like a topological change. They will break up. We can have a quite good agreement. Even after the breakup, we can see this under-resolved interface can also, the tiny bubbles can also be captured here. So we're quite happy that we can resolve this problem. Another problem is the droplet migration due to the thermocapillarity effect. This droplet actually is placed in a linear temperature gradient because of the surface tension is a function of the temperature. It will cause the Marconi flows and make the droplet migrate upwards here. Because when the flow is very viscous or the speed is very slow, at the limit of the low Reynolds number and Kabir numbers, we can expect an analytical solution here, which I give in the middle of this figure here. So we try to compare our numerical solutions with this analytical solution. We can find that no matter different surface tension method to calculate, for calculations, we have a quite good agreement between numerical results and analytical solutions here. The other case is a three-dimensional droplet deformation in simple shear flows. The dynamics is showing on the left. In the middle, we only show this contour of the droplet. The reason is that we want to show that even in these high straddling flows, we can see that the contour of these volume fractions actually are parallel to each other, aligned with each other. That means is we'll keep the equilibrium profile here, ensuring the accurate computation of the normal direction to the interface and the curvature. So we also compare our results with theoretical solutions by Taylor. For these Stokes flow and the small Kabir numbers, Taylor have got an analytical solution here represented by these solid straight lines. You can see at the very small Kabir numbers, our results are in good agreement with the theoretical analysis. When the Kabir number increases, then it will gradually deviate because where the series fails, we also agree with other benchmark solutions from other researchers here. Okay, for this Janus droplet, we need to extend these improved interface flows models to the ternary fluid flow models. I give the equation here. Then we also validated these simulations by comparing against the experiments. This is the droplet at the rest in the fluid initially have a shape like this. When you apply the shear flow to it, then at the most elongated cases, we have these figures here where the numeric solutions are superimposed on the experimental ones, or at the most compression cases, we also have a quite good agreement here. Okay, so then we have some numeric study here. Firstly, you consider two-dimensional cases because this problem is very complicated. You have many parameters to narrow down our research scope. We restrict us to the, for example, the droplet would have the equal size, equal density, and equal viscosities. Also, the drop shape equilibrium is determined by the surface tension coefficient. Here, for this case, we assume that the surface tensions between these fluid 1 and fluid 3, or fluid 1 between fluid 2 or the 2 and 3 are equal. Of course, we can change them. Actually, we'll change the data, but here we show these results here. And then for this fluid system is characterized by these dimension parameters. There's Kabir numbers and the Reynolds number here. Okay, then we consider these dynamics at the low Reynolds number and the Kabir numbers. We show the flow regime here. At the low Kabir numbers, like 0.07, it will have a small deformation and rotated in shear flows. When you increase the shear rate, then you can see that it has quite large deformations. if you keep going, then we can see that the droplet will eventually break up. In these studies, we only focus on the rotation dynamics of this Janus droplet. We can see that the geometric parameters of this droplet can be defined like L. That means it's along this central node of two component droplet. We have this half length, and also we measure the half width of this inner interface here. That's B. So if we track time evolution of these geometric parameters, we can calculate, for example, the average value of L, and we can calculate the magnitude of that L, as well as for the average value of the B or B bar here, or the delta B here. So if we can do this, we can do many calculations, for example, as a function of capillary numbers. For the small capillary numbers, we can see that the average value of L actually is equal to the L of the droplet at rest. Okay, with the increase of the capillary number, you can see that the average value will larger than the initial value of L. Then we call this regime is nonlinear deformation regime, where the L larger than L0 and B bar larger than B0 here. Then we can show that the amplitude of this deformation as function of this 1 plus beta Reynolds capillary here, we can show they are actually form a line that is linear. Why this deformation is proportional to the capillary number, also linearly related to Reynolds one, we can using a one-dimensional mesh spring system to expand this. For example, so we use here because the L, that means the inertia of this deformation droplet is shown here, and we also have this viscosity damping here. We have the spring, that's the subtension L multiplied L minus L bar here. And here, the right-hand side is the force exerted on it, including shear stress and also in the inertia, that's pressure here. So we can do some simplification. For example, the drop in inertia is negligible because its acceleration is very small. And also, if the droplet is at the largest elongation, then we have the L dot equals 0. Then we have this, the L minus L bar is delta L. Then with this simplification, that means we have this linear relation here, as we show in the numeric results. That means this one-dimensional mesh springs can well account for the linear deformation of this droplet when it has the largest elongation or the most compression case. For the pure droplet, Taylor has proposed deformation parameters like this way. Similarly, we can, for this general droplet, we can have a similar formulation like this way. In this way, we can make sure that when a droplet is at equilibrium, D would be equal 0 here. So if we put this definition of deformation parameter here, then we have this form. If we take count of this linear deformation, that L bar approximately equal L0 or B bar approximately equal B0, then we have this simplified version here. First of all, then we put this into the relation of the delta L and delta L. We have this also have this linear relation here. Then we put all the data here. Then we can find that when we have the linear deformation, D maximum must be less than 0.0 here. Then we have non-linear deformation here. All this shows this how the general droplet deformation in shear flow. Then how about the rotation? The one simple question is, can the rotation period of general droplet can be predicted according to the Jeffrey theory for ellipsoidal rotation, because only ellipsoidal particles rotated in the the shear flows here. So let's revisit the Jeffreys series. For example, for absolute droplet, you have an aspect ratio defined as lambda like this way, and its period, rotation period, would have a form like this way. It's related to the shear rate and aspect ratio. Then the time evolution of a Zumos angle phi should have this expression here. In order to correlate our relation with the Jeffrey series for here we have the Janus droplet. In the Jeffrey's cases, that's the particles. What's the difference? The difference is at the surface of the Janus droplet, you would have surface slip there. So what we want to do is, can the slip effect at the interface be approximated by a corrected shear rate here? So then we followed previous work like Badok and Mason showed that for when the inertial is ignored, that's Stokes flows, then we have corrected the parameter the zeta equal initial parameters. Then for correlations for weak inertia, we can expand it to the first of the Reynolds sum, as we have alpha here. So then we can, in our experiments, in numerical experiments, we can also change the viscosities. For example, we change the viscosity of the Janus droplet relative to the surrounding fluids. We can see that the droplet viscosity apparently have little effect on the rotational period. Another thing is that how about aspect ratio of a Janus droplet? Essentially, we have the aspect ratio when droplet have its equilibrium shape. Also, the deformation also change its aspect ratio here. So in our experiments, we change the surface tension so we can have different initial shape of the droplet. For example, when the surface tension of the inner droplet in the interface is much smaller than the outer one, you have this shape very close to the circular shape. Then if you increase it, make it, for example, here would be 1, that means the interface surface tension equal to the outer interface, then you have this shape, or even larger than 1, you will have this shape. When you have, for the simulation at the very small Cubic numbers, so you can see the rotation period seems just increase slowly. But if you increase the Cubic number to 0.1, you can see in the linear deformation regime, it doesn't change much, but in the nonlinear regime, it changes significantly. So we have to take account of the drop deformation here. So then we calculate the effective aspect ratio of Janus droplet in such a way. That means actually the aspect ratio of droplet at the most significant elongation state. Then we replace the correlated shear rate and the effective aspect ratio into Jeffrey series for these particles. It would have a function like this, how good it is. So we put our results, the theoretical prediction here, also the numerical results. That seems all the results collapse onto a single curve. That shows that actually our theory seems to give a quite good prediction here. Also, if we have this theoretical prediction of this rotation period, we can also predict the time evolution of azimuthal angle here. That's how rotated with time. So we put these results here, then we compare the prediction with the numerical results. The prediction is using the dashed lines. Here, see at different Cubic numbers. The small deformation and large deformation, we have a reasonable agreement here. Okay, this is for the two-dimensional simulations. Then we came to the three-dimensional ones. Because in two-dimensional, the deformation and rotation always consistent with the plane of where shear applied. For the three-dimensional case, it also have a different problem. That means the angle between the axis and the incoming flow could be different here. Also, we can see a different drop shape here. We have two different initial drop shape here. One is we call it the dumbbell shaped Janus droplet. That means the surface tension sigma 1, 2. That means the surface tension at this inner interface is approximately similar to the surface tension at the outer interface. That's sigma 1, 3. Remember that sigma 2, 3 equals 1, 3 in our numeric setup. Okay. The other case is if we assume that this surface tension at the interface is much smaller than that one at the outer interface, then this general droplet would be very close to a pure droplet. That means almost isotropic shape. That's a spherical here. Okay. The other one is the orientation of the general droplet. Here it would be described by a position vector D, as I shown here. D is represent a vector pointing from the central node of the component droplet 1 to this central node of the droplet 2. Here we connect these 2 points. Then we have this vector, position vector D here. Then we can, with this D, we can define this polar angle zeta and azomorph angle phi here. Okay. So, okay, and here is the problem statement of our problem. We also consider component droplet of equal size, density, and viscosity. And the dimension parameters would also be the Cabir number and the Reynolds number here. So I show you some results here. This is the time evolution of dumbbell-shaped general droplet in shear flow. You can see that it has some orbit drift of general droplet from continuously from the low orbits. That means the zeta, the polar angle zeta, is small. Here, initial polar angle is 30 degrees here. It will gradually migrate to the high ones until reach the zeta equals 0. Why we have such case? Another case is evolution of a near spherical general droplet in shear flow. It will deform, it will migrate. Similarly, it doesn't move at all and not deformation at all, because from these views, actually, it's hard to see the change of the the interface movement. So we see in other way, you can see it's also migrate, but in the very different direction compared to the dumbbell-shaped droplet. That means for this kind of droplet, it drifts from high orbits to low ones until reach zeta equals 0. That means depends on the aspect ratio of the droplet at the equilibrium. Its orbit drifting could have a bifurcation here. So I show this bifurcation. For example, we have the same Reynolds Cabir numbers and initial polar angle here. And what we change is only the surface tension difference. For this one, it's dumbbell shape. It will goes up, increase, oscillate until it's reached to the orbits of zeta equal 90 degrees. For this nearly spherical shape, that's this one, it goes oscillate, goes down, down, down. Although it doesn't reach 0, but we can see its approach asymptotically goes to 0. But for this aspect ratio in the middle, like these 2 shapes, can see its evolution very slowly. Nearly doesn't change with time. What happens here? What's the mechanism of this orbit drift for this different kind of general droplet? So you can do some analysis. For this dumbbell drop, actually we see that the coupling between the outer interface deformation with the surrounding fluid is very important. Due to the surrounding fluid field, it will stretch it, make it deform, elongated. So that means its aspect ratios increase. When its aspect ratio increase, just like Jeffrey's particles, it will try to move to high orbits. But when you travel to high orbits, actually the projection, the area of Janus droplet projection onto an XY plane, where the shear planes increase with time. So does the shear force exerted on this droplet. That means it makes further elongated. So the information keep increase until it's reached 90 degrees, where the deformation becomes the maximum. That's why this orbit drift like this way. However, for the drift, orbit drift mechanism for this near spherical droplet, you can see that for this kind of droplet, actually because the surface tension is much smaller than the outer interface, so it's nearly like a pure droplet. That means it will the shape. I mean the shape, the droplet as a whole, nearly reach a steady state. Not doesn't deform with time. Doesn't change with time. It's reach a steady state, but the inner interface changed with time. Okay, so you can imagine that because the inner interface, it has some difference. I mean, it's not symmetric with respect to the Z0 plane here. If there's difference, biased, then it would drive by this hydrodynamic torque from the vortex enclosed within this droplet, like this one. Okay, such a balance will drive this interface to the other direction. That means the theta 0 equals 0 in this way. So until these zeta equals 0 planes coincide with this inner interface, then the total torque would be balanced. So then it will reach the final state, which is the lowest orbit of this Janus droplet. Okay, so that's the explanation. So okay, now can come to my conclusion here. The conclusion, yes, one can see that depends on the aspect ratio of the Janus droplet at equilibrium. Rotation droplet in shear can only have two steady orbits. It's 90 degrees or 0 degrees. Also, the process of orbit drift is determined by the interplay between the deformation of the outer interface or the inner interface and the rotation of the Janus droplet. With weak inertia, the rotation period can be modeled by Jeffrey series for ellipsoidal particles. Although I didn't show the results for the three-dimensional orbit droplet or three-dimensional droplet here, actually we have done such research. We can show that it indeed can be modeled by the Jeffrey's series for the ellipsoidal particles. Here I give some perspective because the problem is very complicated. For example, what's the coupling among multiple Janus droplets in shear? This is very important, just as shown by the Professor Montati just now. If you consider a dense multifaceted flows, you have to take account of the coupling between, because the droplet could be so close, you have to take account of coupling or interaction between these Janus droplet. Also, we can have other asymmetry of Janus droplet here. For example, the density, the one component droplet could be more denser than the other one, or its viscosity higher than the other one. So many asymmetricity can be considered here. The final objective is our research is what's the rheology of the relevant multifaceted flows. If you take, so you have a flow system have so many Janus droplets, what's the macroscopic property of these multifaceted flows? Okay, so now let me thank the collaborators here. That's our former PhD students, also our colleagues here, and especially the Professor Horan Liu, Professor Li Junquan, and Professor Peng Gao here. Thank you very much. I think I'm ready for questions.
Oh, yes. Thank you very much, Professor Hang. Very, very insightful talk. Very fundamental, actually. We moved from larger scale analysis of multi-phase systems to a very attentive and very careful modeling of microscopic effects in the shear flow. Thank you very much. Very, very insightful. Now the talk is open for questions. Do we have anyone asking questions live? I see no one actually raising questions. We have one from Jun Yao, from Professor Yao, in the chat. I'm going to read it. For the interesting phenomena mentioned in the talk, the orbiting transition of Janus droplet, do you also find it in experimental way?
Yeah, so here we didn't perform the experiments, but other research did. As I show in, let me see, I think have in validation of numerical methods, we have a case here.
Yes, 26, yeah, 25, yes.
Yes, this case, actually, this experiment has done long time ago, but I think it's 1972. We